All right, so for the benefit of the folks watching online, I'm going to draw the diagram that you've seen many times, but they haven't, or at least they haven't seen me do it. So you're going to look at an object, and I'm just going to draw the object as an arrow. And you're going to see light coming from the top of the object and the bottom of the object. That's perspective. The odd notion that we don't see physical size, we see angular size. Because and photographers, filmmakers take advantage of this all the time to make things look surreal. So what we see is the angle, which I'll draw as a theta, but the object itself has a physical size and it's also going to be a certain distance away. So we got a capital D and a little d on your formula sheet for this. It's very common for people to mess up which is which. One trick another instructor taught me was, well, if you're going to draw an object, a circle with a diameter, you start off by making a D, a capital D, and you just keep going all the way around. So the capital D refers to the diameter of like a spherical object. So, there is a way to figure this out with trigonometry. You're welcome to use it if you know that, but you're not expected to know trig in this class. So we recognize that theta, and let's say D approximates the same angle way out here, because as you get further and further out, the arc flattens to the point that a straight line can approximate it reasonably well, so that these two angles are congruent. All right, that means the ratios are going to be the same. So the ratio of theta to the full angular size of the red circle, theta over 360 in degrees, is going to be equal to the ratio of the diameter to the full circumference swept out by the circle of radius d. Okay, so the circumference is, so the ratio is that approximation of the arc length that's drawn in red, which is the physical size, d, divided by 2 pi times little d, which is the circumference of the blue dotted circle. Make sense? So, I have data for the sun in front of me, so I'll do that real quick. We want to know, say, the angular size of the sun. That's on one of your worksheets. Okay? So we'll punch in theta. Again, all I'm going to do is do an algebra trick where I move the 360 over to the side by multiplying both sides by 360. We all good with that? And for my online students, I'll just be a little more clear about that and do this. Now the 360 cancels out over here, and that leaves theta, the thing that you're interested in. So, rearranging this, I'm going to put I just like to have the numbers out in front of symbols. I don't know why. I'm just picky that way. For the sun, 360 times the diameter. Now what unit to use you have a bit more flexibility. You don't have to go all the way down to SI in this case. You don't even have to use SI. You can use miles or even light years. As long as whatever unit to use in the numerator, use the same units in the denominator. That way they'll cancel out. So if you're dealing in astronomical units, that's fine, as long as that's an AU and that's an AU too. So my formula sheet has the mass of the sun, radius of the sun is 6.96 by 10 to the 5 kilometers. And the distance to the sun I don't have in front of me, so I'll have to ask Siri. I could use the iPad.
Don't you want diameter?
Yeah, wouldn't we have to times that by 2? Multiply.
That is the that's the radius. Yeah, you're right. I needed the diameter. If I had a nickel for every time I confused radius and diameter. So we're going to double that. 2 times 6.96. Good catch. Still need to know the distance. What's the distance to the sun in kilometers?
The distance from the sun to Earth at 1:34 p.m. Eastern Daylight Time, Thursday, September 12, 2019 is about 151 million kilometers.
151 by 10 to the 6. All right, so I can tell you the answer to that is about 0.49. But go ahead and punch it into your calculator and convince yourself. Now, how do I know that? It's a good number to have memorized. One of the reasons why we have solar eclipses is that even though the sun and the moon are wildly different sizes, physical sizes, their position in space gives them the same apparent angular size, which for the moon is about 0.52 degrees, and the sun is 0.49. So they're not exactly the same, but they're close. So that when the sun and the moon line up, the moon can totally block the sun and eclipse it. Now, why am I bringing this up? I was talking about goalposts a little earlier, because you're going to see this problem come up a lot. We're going to throw you on Mars or Venus or whatever and ask you what the size of the sun is, apparent size of the sun. Just know that the closer you get to something, the bigger it appears. So the bigger the angle that it's going to sweep out is going to become. Theta gets bigger the closer you get to it. So if we throw you on Mercury and ask you what the size of the sun is, your apparent size of the sun, you better get something that's bigger than half a degree. If you don't, you've made a mistake. If we throw you out on Mars, Mars is a superior planet. It's further out from the sun than we are. You need to get something less than a degree. Yeah?
Every single time I calculated it, like even different ways, I'm still getting 1.18 times 10 to the 17th. Yeah,
I got 0.52.
10 to the 17th.
yeah.
There's no way. This is divided by that. This is 10 to the 8. That's 10 to the 5. You're getting 10 to the, 1, 2 over here. 10 to the 7 divided by 10 to the 8. You should be getting something over the order of magnitude 10 to the minus 1. 10 to the 17, something's goofy.
We're doing 6.96 times 10 to the 5th times 2.
Yeah. So yeah, all right. So again, I'm doing order of magnitude approximations, so I'm forgetting about this stuff. So yeah, that's probably going to knock that up to 10 to the 6. But then this guy's got 2 pi out in front of him, so
Is 0.52 close enough?
yeah. Well, that's pretty close to that. Maybe I got it backwards. Maybe I got it for the sun it's 0.52 and for the moon it's 0.49. Yeah, one thing you can notice is that this 2 is going to cancel with that 2. Yeah, mean distance from the Earth to the Sun.